Okay, good morning to everyone. This is the seminar number 9 of the 2022 seminar series of the Magnetic Resonance Laboratory. In this opportunity, we have an invited talk that is going to be given by Antonio Azevedo. So now I will give pass to Fernando Machado, so he can make the introduction of our speaker this time.
Are you kidding? Fernando is there?
Hi, Antonio. A long time, you know. Nice to see you again.
I
Yeah,
saw
it's
him 2 minutes ago.
yes, it is a great pleasure to introduce my colleague Antonio, and I thank you, Carlos, for inviting me. I made some notes because Antonio works too much and has many contributions. So I will read some of them. Professor Antonio Azevedo, he did his undergraduate work in electric and electronic engineering at the Federal University of Rio Grande do Norte. It's a nearby state. Then he came to Recife, where he completed his master's degree in science, in physics, in 1987. Continued his education. He completed his PhD work in here as well in 1991. And then he left to the Carnegie Mellon University to work in the data storage system center. This was a postdoc in 1992 until 1994. When he came back to Recife, then he became a professor in 1996 and is here since then. Nowadays, he is a full professor and he contributes in many administration of the department, like the head of the Physics department. He was the head of the undergraduate office, among others contributions. Currently, he is a member of the editorial board of the Journal of Magnetism, Magnetic Materials, and of the IEEE Transaction Magnet. Antonio was recognized by the American Physics Society as an outstanding referee in 2017. He has published over 150 papers, has an H factor of 30, and more than 3,000 citations. He wrote also 2 chapters in specialized magnetism books. Antonio supervised about 20 graduate students among master and PhD, and half a dozen postdocs. He contributed largely in topics such as chaos, exchange bias, giant magnetic resistance, and more recently, spintronics, among many other topics. But what impressed more about Antonio is that he's always present in the lab on a daily basis. He is a hands-on physicist with great expertise in preparing sample and develop instrumentation as well. So today he's be talking about Orbitronics, spin and orbital Hall effect. So Antonio, please.
Thank you, Fernando.
Thank you, Fernando, for the presentation. Now you can share your screen, Antonio. I think everything's okay now.
It's coming.
Yeah, it's coming.
It's okay?
Yes, it's okay. You can go ahead.
Ok. Fernando, muito obrigado pela gentil apresentação. Okay, good morning, everyone. I can't see you, but I hope you can see me. First of all, I would like to thank you for the invitation. Unfortunately, this seminar cannot be held in person, but despite Recife being about 5,000 kilometers from Bariloche, we can talk as if it were in person, okay? And what I'm going to talk to present you are the experimental results that explore the effect of Miop coupling. But before, in the first part, in benefit to the students, I will review basic concept. In particular, I will give you an overview about Hashbar and Hashbar Edelstein effect, which are important effects was used in spin charge interconvection in magnetic nanostructure. In the second part, I will present you the idea of how orbital angular moment is being considered as a major player in the area of Orbitronics. And then I will include very challenging experimental data that we have just submitted for publication. So I'll try to follow this outline. And okay, I guess most of you are familiar with the spin charging interconvection induced by Miop Coupling, where the 3 degrees of freedom, charge, the spin, and orbital, can be connected together. These degrees of freedom are also coupled to temperature, to electromagnetic radiation, and eventually to electric polarization. Okay. By the end of this talk, I hope that the final message is that we can use these phenomena, the 3 degrees of freedom, to control the magnetization in multi-layer system, in nanostructure system. Also, we can use charge spin conversion to detect, to switch, or to couple the magnetization nanostructure. This is the final message that I would like to, at the end of my talk, I'd like to give you. So the term spin orbitronics appeared many years ago. There is a good review paper which was published in 2015, in which this figure shows various realizations of various phenomena connected to spin orbitronics. When spin orbitronics, spin coupling is present in a system with broken inversion symmetry, for instance, in interfaces or thin films, there appears very unique transport properties that gave birth to a tremendous field of spin orbitronics. And so this is the art, state of the art, to manipulate spin using spin-orbital coupling. And so this figure here illustrates several subfields, which include a spin Hall effect, which is very known, a spin transistor, spin optic qubits, and quantum spin Hall, and so on. Let me change this guy here. Okay. Topological insulator, direct materials, etc., etc., etc. So in this figure, it's very illustrative the effects that the spin orbitronic can be present. So let me see here. Actually, for instance, in the spin Hall effect, which is an effect that separates spins, inducing the spin accumulation in the edge of the sample. It's already used in applications, commercial applications, so on. So I use the student, so the student can go in this paper. It's 7 years old, but it's still a very good one to review the spin orbitronic area. Let me now switch a little bit to tell you about the difference between conventional magnetics and spintronics. Actually, spintronics is based on the use of the spin-optic coupling, which is a quantum effect, instead of induction, which is a classical effect. So conventional magnetics normally use induction effect, and the spintronic use a quantum effect, mainly spin-optic coupling. So if you write the Hamiltonian of an electron submitted to an electromagnetic field, we have the kinetic energy term plus potential. We have the Zeeman energy term, which couples the spin with the field, the magnetic field. And the last term, we have the spin-Miop coupling, which couples the spin to linear moment and to the electric field. So in solid, spin-Miop coupling is structure dependent. It's important in translational symmetry breaking systems such as surface, interface, and so on. And it's very important. So if we take this last term and we can rewrite it in this way. So the spin-Miop coupling term is proportional to the dot product of angular moment, spin angular moment. So in atoms, it's proportional to Z, and in solids, it's a structure-dependent symmetry. So the inversion asymmetry in materials is very important to drive spin-Miop coupling. Now, let me show you a little bit, for instance, how the spin-Miop coupling, for instance, we may have the spin-Miop coupling in solids. For instance, when an electron in a surface, in surface, normally we have perpendicular electric field due to the dangling bonds up or down, so we have an electric field. An electron in this surface, we will see in the reference frame of the electron, it will see a magnetic field, an effective magnetic field, which is proportional to this vector product here. And the spin-Miop coupling is, if you take it some interaction, it's very weak one, but it's very powerful. As I'm going to show you here, the example of the spin-Miop coupling effects that ranges from magnetocrystalline to anti-symmetric exchange. This is the Biologinski-Moria, magnetic damping, AMR, anomalous Hall effect, spin Hall effect, and so on. For instance, for spintronics, these effects are very important. They play a very important role. So there are two types of spin-Miop coupling solids. One is symmetry independent, which is intrinsic. This is responsible, for instance, by the doublet in sodium. And there is the symmetry dependent, which is extrinsic. So it exists in crystals with breaking the spatial inversion symmetry. For instance, there is this bulk effect, which is bulk-induced asymmetry in some kind of materials, zinc blend materials, for instance. And there is the Hashbar interaction, which appears in surface, which is a surface-induced asymmetry. So we are interested in this talk, in this last one, which is Hashbar interaction, which is driven by the break of the translational symmetry. Let me go a little bit ahead here. So this is what I was talking about earlier. In surface, we have naturally we have an electric field due to the dangling bonds. So if you expand the potential here, we have a term which is proportional to the electric field. This is the gradient of the potential. So due to this electric field, the electrons in the surface see a magnetic field, which is given by this expression. So in the reference frame of the electron, the magnetic dipole moment is submitted to this energy, which is Zeeman energy, which is proportional to this term here. So this is this Hamiltonian here is called Hashbar Hamiltonian. So surface states are very sensitive to this field, and it can play a very important role in materials in magnetism. So you can solve a very simple quantum mechanical problem if you add this Hamiltonian term to the kinetic energy. So in a two-dimensional electron system, we have the kinetic energy and the Hashbar energy. So if you just take the kinetic energy, the electron with the spin up and the spin down, opposite spins are degenerated. But due to this term here, we have the degenerescence is lifted, and the energy is separated in K. This is the contribution of Hashbar to this effect. So if you take the dispersion relation in 3 dimensions, we have this kind of system. So the dispersion relation is shifted along the K, and it means that this lift of the degenerescence due to this effective field, so we do not need to apply an external field. So it means that the spin and the linear moment are locked. So this is an example here. So normally the spin are perpendicular to the moment in this reciprocal space. So this is a very important achievement, which has been used lately in spintronics. So one of the applications for this Hashbar effect field was proposed in 1990 by Data and Das, which is illustrated here. In this case, we have a current which flows to this structure here. The current is polarized in the first layer, and it flows to this two-dimensional electron gas, and due to the magnetic field, the spin rotates, for instance, of 180 degrees. If we apply a voltage, so the electric field can increase and the magnetic field can increase, and instead of to have 180 degrees, we have 360 degrees. And actually, the Hashbar, the data DAS transistor is illustrated in this animation here. So when the electron flows from left to right, it rotates, for instance, 180 degrees due to this electric field applied. If we decrease the electric field, it rotates only 180 degrees, and the current can be controlled just by applying a voltage potential, in a similar way as the field effect transistor. But in this case, we are controlling the state of the spin. So this is a very illustrative effect, but unfortunately, it's very difficult to be developed. So this is the Hashbar effect, the Hashbar field. The Hashbar Ldc effect, it was published in 1990, in which the authors, in this paper, the authors say that the spin polarization of conduction electron induced by electric current in a two-dimensional material can induce and spin magnetization. Here I have an animation. What is direct Hashbar Ldc effect? We have an injection of a charge current in a two-dimensional system. It generates a spin accumulation in this surface. For instance, this is the animation. Whenever we have this in equilibrium, the Fermi disk is centralized, so in equilibrium. When we apply a current, the Fermi disk shifts a little bit, and it overpopulates the spin up and deplete the spin down, so it creates a spin accumulation directed to y direction. So in this case, we are injecting a charge current and created a spin current. The inverse effect, in this case, we inject a spin accumulation and it creates a charge current. So in both effects, this is called the Hashbar Ldc effect, which now is becoming a very important effect in spintronics. So there's a figure of math that I can talk later. Now let me move to this, how a spin charge can be converted each other by effect of the Miop coupling. The first effect which was proposed theoretically many years ago by Diakonov and Perel, and he discovered in 1999 by Hirsch. It was experimentally detected in 2004. Is the following: we have a charge current which flows along a large Miop coupling material, and there is this spin-dependent scattering represented by this green dot here. So in this case, the current, the spin up and down they are separated in the transverse direction. So in this case, we have a charge current creating a spin current, transversal spin current. And in this case, we cannot detect any voltage difference, but we have a population, a spin population with opposite direction at the edges of the sample. So we can detect this effect just by means of an optical effect, like for instance, magneto-optical carrier effect. The rotation, the polarization rotates for one direction and rotate for the other direction, depend on the spin population in that region. There is another effect which takes advantage of the inverse spin Hall effect, which is a combination of driven spin pumping by ferromagnet resonance and this inverse spin Hall effect. In this case, we have two layers. The magnetization is put to process by the ferromagnet resonance. It injects a angular moment accumulation, spin accumulation into the adjacent layer, which is heavy metal layer. And due to the inverse spin Hall effect, it creates a transversal charge current, so we can measure the voltage in this condition here, perpendicular voltage. So this is an example obtained by lithium iron garnet platinum. This is the ferromagnet resonance signal. This is the voltage measured at the ferromagnet resonance signal. There's another effect which is called the spin-Zibek effect. In this case, the spin pump is driven thermally. So here we have the spin is coherent pumped, and in this case, the spin is pumped in an incoherent way, just by thermal effect. We apply a thermal gradient perpendicular to the system. It injects a spin current, and due to this inverse spin Hall effect, it creates a voltage here. So if we sweep, for instance, the magnetic field up and down, when the magnetization switches up and down, we can measure a voltage from here to here, a voltage difference, which is similar to the magnetization curve. There's another effect, is Hashbar Ldc effect that I was talking about. In this case, we have a electron in a surface, an interface, two-dimensional system, and there appears a electric field perpendicular to the surface, and so there appears a interaction between the effective magnetic field seen by the electron at its reference frame. So in this case, we have the separation. We have the degenerescence is lifted due to this effect. And as I shown before, in this case, when we apply a current at the surface of the interface, it creates a spin accumulation at the surface. So let me go quickly to this slide. What I would like to show you here is that to make spin pumping is trick if you are using ferromagnet metals. Ferromagnet metals normally have a component which comes from galvanomagnetic effect, so due to the self-induced spin charge current. So a good system to investigate the spin pumping should be made by a ferromagnet insulator, such as yttrium iron garnet, and a heavy metal material. So in this case, the spin pumping signal is very symmetrical, and we can get rid of this galvanomagnetic effect and self-induced spin charge conversion, which are present in ferromagnetic metals. So now, after this brief introduction directed to the students, I'll show you some results. Let's see how my time is. Okay, I'll show you some results, and in the second part, the orbital Hall effect. So let me show you his result of yttrium iron garnet graphene. Graphene is a two-dimensional material, very well known material. So in this case, to prepare a single graphene layer into a egg film, we have to make several steps. First of all, the graphene layer is synthesized on top of copper, and we deposited the PMMA layer on top of the graphene layer, and later we remove the copper just using this acid used to remove copper normally, and we have a cleaning, and so just putting in the single layer graphene with PMMA, it can be transferred to the egg film. So in this case, we have the egg, single layer of graphene, and PMMA is still there. So the PMMA can be removed just by acetone, and later we have this very nice bi-layer system, which is made by yttrium iron garnet and a graphene layer. So this is a STM image obtained in our system, which is graphene layer deposited on top of yttrium iron garnet. And for instance, it's very smooth layer. And for instance, we can make Raman characterization, and the graphene is there. So later we measured the magnetoresistance, just conducted magnetoresistance measurement, and we detected that the graphene, despite not being magnet, due to the proximity effect, it acquires a magnetic property. So later we have carried out a spin pumping measurement, and graphene in this case can convert the spin current in charge current, because in this system here, there is no metal here. So it's yttrium iron garnet, which is an insulator, and on top of it, there is a single layer of graphene. So in this case, we inject a spin current in graphene, and it converts into a voltage. So we characterized the effect. We also repeated the same measurement instead of using graphene, instead of using yttrium iron garnet, we use permalloy, which is a metallic alloy. In this case, the spin pumping signal has to be well analyzed, and the effect is the same. So what we have shown is that the graphene, despite not being a large Miop coupling material, it can convert the spin in charge just by due to this proximity effect. Later, we also conducted experiments in this material, MOS2, which is a direct gap semiconductor, very, very, very well thin. And in this case, for instance, here I'm showing you the MOS2, which was transferred just by exfoliation to the surface of the egg, and later we deposited contacts, electrodes, gold electrodes by lithographic process, and this is the ferromagnet resonance at the berry egg film, and after deposition of MOS2, the line width increased a little bit, so you can see the quality of this egg is very nice, 0.34 worsted, the line width. It increased a little bit because in this case, when we inject the spin current to the MOS2, it's lose it, so the ferromagnet resonance in there appears an additional damping due to the spin transfer. So we measured this spin pumping signal, and what we have shown is that in spite of being a semiconductor material, very thin one, it also converts spin in charge. This was published a few years ago. And also, let's move to the next one. This is a hybrid structure made of a topological insulator and a permalloy. The topological insulator was fabricated by the group of Professor Jagadish Mudera at the MIT. So he is one of the experts in this kind of system, and he sent us some samples which are composed by these 6 quintuple layers of this chemical composition here, and we deposit just on top of the sample an island of permalloy, and you also add the 2 electrodes, and we measured the ferromagnet resonance of permalloy. It has an asymmetric component which is due to this magnetic galvanic effects and so on, but this is clearly a signal which comes from the conversion of the spin to charge current. And we also measured the spin-Seebeck effect, in which we applied, in this case, we had to insulate the permalloy from the topological insulator by nickel oxide layer to avoid the anomalous Nernst effect. And we measured a very weak signal due to the spin to charge conversion by this thermal and spin pumping effect. So all the characteristics are there. So we published this many years ago. And more recently, we published some papers in which we also deposited this material, which is considered a topological insulator by sputtering, and we also measured that even by deposit by sputtering, it conserves these topological insulator properties, which conductors at the surfaces and in the bulk is insulator. So we made the characterization, X-ray characterization, and we detected that in this case, this material converts the spin to charge with the opposite signal as platinum. For instance, platinum converts spin to charge with a spin Hall angle, positive spin Hall angle. Tantalum is a negative spin Hall angle, and Bi2Se3 has the same signal as tantalum. We published this paper last year, and we made several measurements. And so this is I have just shown some results in which we investigated the spin charge conversion in conventional materials, or in a conventional way. So now let me move to a more challenging phenomena. So the first part was what I called the spintronic conventional phenomena. Now let me move to what we are calling the orbital Hall effect. And before to go to the topic, I would like to show you very intriguing results. For instance, this is just platinum, yttrium, iron, garnet. This is the spin pumping signal measured at the ferromagnet resonance in a very conventional way. In this case, we are showing the current because we divided by the electrical resistance of platinum, just to avoid problem of contact and so on. And when we covered the platinum layer with copper oxide, we measured a very high enhancement of the signal. So red signal is just conventional spin pumping measurement, yttrium, iron, garnet, platinum. And we cover with the copper oxide layer, very thin one, 3 nanometers. I can give you details of this process later. The signal increased by about 4.5 times. So the enhancement after capping layer of copper oxide cannot be explained easily. And we also measured the same samples using the thermal spin pumping or spin-Seebeck effect. In this case, this is the spin-Seebeck effect curve just measured in platinum, yttrium, iron, garnet, platinum. As the field sweeps up and down, the magnetization sweeps up and down, and we measure the voltage here, which is similar to a magnetization curve. When we put copper oxide, we detected an enhancement. The enhancement is a little bit smaller, it's half of the enhancement obtained by spin pump effect, but we also obtained a significant enhancement of the signal. It's important to keep in mind that the two techniques are a little bit different. When in the ferromagnet resonance spin pumping, we are injecting a coherent spin current. In this thermal-driven spin pumping, we are injecting a incoherent spin current. Charles Chien from Johns Hopkins University has called the attention for the difference between two effects. It's important so the student can keep in mind that they are a little different. So the question is, I have two questions now. Why is this phenomenon important and how to explain it? The phenomenon is the increase of the spin to charge current conversion when we deposit the copper oxide layer on top of the platinum layer. The first question is, so to answer the first question, let's remind you the spin transfer phenomena, the spin transfer, transfer torque and spin-orbit torque. To those who are familiar with the concept of spin transfer torque, I would ask patience. But the idea behind this phenomena is the injection of a polarized electron beam into a ferromagnet material. And so after interacting with the local magnetization, the outgoing electron beam will have the spin rotated to become parallel to the local magnetization. And as the total angular moment is conserved, there will be a back action torque in the magnetization. This back action torque is called spin transfer torque. This was proposed theoretically many years ago by Berger, Luc Berger, and John Sloan-Zuss. Two theoretical papers separated at the same time. And this was 2 years later, it was discovered experimentally. And one way very convenient way to investigate this effect is by fabricating a pillar made of 2 layers of ferromagnet material separated by an insulator. The fixed layer, the magnetization is fixed, and when it's used to polarize the spin. So by transferring torque from the fixed layer to the free layer, the magnetization of the free layer can be manipulated just by electron means with no need of magnetic field. So this effect was proposed as an application of STT magnet random access memory bits, in which the read and write current flows through the same path. But in the last decade, there appeared an alternative scheme that doesn't use the polarizer layer anymore, which is Miop torque, which is a spin-orbit coupling driven phenomenon. So in this case, actually you have 2 schemes. One is a spin Hall effect, in which we have 2 layers, a bilayer, and we flow a charge current to the large Miop coupling layer. It creates a spin current, perpendicular spin current, so it can transfer torque to the top layer, the top magnetization layer. So the other scheme uses the Hashbar Hamiltonian effect, in which we flow a current, and the current that flows through the interface, it creates a spin accumulation that eventually can be injected into the magnet material. So using both schemes, we can transfer torque to the magnetization, and the magnetization can be manipulated just by passing just flowing current into the bottom layer. So in this case, the bit of MRAMs is most simple. It's simple developed because the write current passes just at here, and the read path flows through the bit. So in this case, we can use very weak charge current. In this first scheme here, the STT MRAMs, normally the charge current is very large. And for the large shock materials are normally used platinum, tantalum, tungsten, and topological insulate, and so on. So this is the reason why discover materials and process that have large spin-to-charge conversion values are important. So this answers the first question. So the first question is answered now. So the discovery of materials and process that increase the spin-to-charge conversion, it's important to develop devices such as those ones that I have just shown. So how to explain it? How to explain it? It's a little bit difficult. Let me show you the first time as the word spintronics appeared in the literature. It's in this paper of 2005, which was written by very important theoreticians, and they have shown that in p-doped silicon, which has no spin-off coupling, when we apply a electric field, it can create the orbital current in a similar way as the spin Hall effect. So this is the first time as the word Orbitronics appears. A few months later appeared this very nice paper also from the people from Japan, in which they have shown that in transition metals, there is a large anomalous Hall effect. And they attributed to this large anomalous Hall effect as due to the orbital currents, in addition to ordinary spin currents, spin current, charge currents. So these are theoretical papers. The other theoretical papers, which was published a few years ago, is this one here, which is intrinsic. Look at the title: intrinsic spin and orbital Hall effect induced by an orbital texture. So this, take a look at this first name here. I will come with him later. In this case, they have shown that an orbital texture can create an intrinsic orbital Hall effect. So in a similar way as the intrinsic spin Hall effect. So, and this orbital Hall effect can occur even in material with no spin-off coupling. And it can be converted into a spin Hall effect in large spin-off coupling materials, such as platinum, for instance. Before to go to the main results that we have shown, that we have investigated here, let me show you a slide of fundamentals of angular moment carriers in solids. Normally in solids, we have local magnetic moments in 3D materials, for instance. We have Ldc, we have orbital and spins. These are normally the carriers of angular moment in solids. This orbital and spins, degree of freedom, can interact together by spin-off coupling. The spin and local moments, local magnetic moments, can interact by exchange interaction. And orbital can interact with Ldc by the crystal field potential. So in this case, when we apply an external field, electrical field, it couples to the orbital. And so this external field can somehow interact with the local magnetic moment and the spin and Ldc just by these different couplings. In this case, the orbital degree of freedom, it's a very important key, a very important player in mediating the interaction between Ldc and spins, and so on. So this is the idea behind the orbital Hall effect. Because at the first time I was reading about this issue, I was worried about because in solid, the angular moment is suppressed. But it can be different of zero. For instance, in equilibrium. In equilibrium, this is the electron orbital distribution. Actually, this is very known from the electronic structure community. For instance, it has radial distribution of charge and tangential distribution of charge. When we apply an electric field, the firm disk, the firm surface shifts a little bit. And so in this case, for instance, this orbital, which is parallel to the firm disk, it shifts into the direction here. And this, in this case, this orbital can be written as a linear composition of the tangential and radial components. If you leave the time evolve as the time evolves, these two components evolves, and by making a very simple calculation, we can calculate the linear moment of this in this system. So, and there appears a finite moment. In this case, this finite moment is it represents it like this figure here. So the angular moment which points out of the figure moves up, and the angular moment which points to the entering in the figure, it moves down. So in this case, what we have here is just a orbital Hall effect, in which when we apply a current, the orbital moments up and down will be separated in the opposite direction. So this is the family of Hall effect family, and there was one which was missing, which is the orbital Hall effect. And the orbital Hall effect can be measured in using different schemes. And the first experimental works are this. The first experimental work is this one, is 2 years ago, in which they use transport measurement in a material made of a ferromagnet insulator, similar as lithium iron garnet, platinum, and copper oxide. And in this case, what they measured, they measured the torque transfer from this electric current which flows to the platinum to the magnetization of this ferromagnet material. I'm just finishing, a few more slides. And actually, this is an indirect way to measure the effect. And this year, a few months ago, appeared this paper, which is editor's suggestion, in which they observed the orbital Hashbar Edelstein. They observed the orbital Hashbar Edelstein effect. So, I mean, in this case, at the interface between the oxide, the copper oxide, and platinum, they detected a orbital Hashbar Edelstein effect. And actually, they measured the anisotropic magnetoresistance, and also they have shown that it depends on the copper oxide, but also is a very indirect way to measure this effect. So now let me move to the results that we have just submitted to publication. Our experiment was performed using 2 series of samples. One is just lithium iron garnet 14 nanometer thick. On top of it was deposited several layers of platinum varying the thickness. And the other series of samples is exactly this one here, but deposit on top of the platinum, we deposit copper oxide. And we investigated this system just by using FMR-driven spin pumping and thermal-driven spin pumping. So the egg films are grown by liquid phase epitaxy, which is very convenient technique to fabricate very nice films of lithium iron garnet, and the platinum and copper were deposited by this system. And there is an important information here. Copper is left 2 days in contact with the air for natural oxidation. If we deposit just copper oxide from a copper oxide sputtering target, the phenomenon doesn't happen. We do not understand why this is happened, but it happened at the same phenomenon happened in the two previous papers that I have shown. So we make the structural characterization by using this glancing angle X-ray diffraction. We detected, for instance, in this case, we deposit a thick layer of copper, and we left it to oxide. And as the copper is actually is thick because we would like to use X-ray to detect the oxidation process. And we can see here there are copper oxide peaks coming from the copper oxide process. So our process is really, we can really get copper oxide layer just leaving it at ambient conditions, in air, just in air. In this case here, we deposit on top of copper a platinum layer just to protect the copper layer. So in this case, we didn't detect the peaks coming from the oxide, the oxidation process. And also we investigated using scanning electron microscopy, and this triangular form of the copper is an indication that the copper is growing in a textured way. So our sample were characterized by this structural characterization, and later we did the thermal spin pumping process. So we injected we apply a thermal gradient perpendicular to the sample, and we measured the spin-Zibek effect, as I shown before. For instance, in this case, we are showing the spin-Zibek effect for different difference of temperature between the top layer and the bottom layer. And this is the slope. This is actually this is the difference between this signal in the signal as a function of the temperature difference. And we can see here that in black symbols were obtained with the sample in which we use copper oxide, and the red ones were obtained just by platinum. And the difference, the slope difference between these two slopes here are due to the presence of the copper oxide. We also measured the signal as a function of platinum thickness, and there is an enhancement here, very significant enhancement of the signal due to the presence of copper oxide. As the platinum layer thickness increases, the two signal becomes the same, and the signal due to the copper oxide presence becomes the same as with no copper oxide. So this is the most important result obtained by thermal spin pumping. We also performed the same measurement using this ferromagnet resonance driven spin pumping. And as I shown before, this is the signal obtained. One important message here is that a pure spin pumping signal has to obey this equation here. If it does obey to this equation here, maximum at 0 degrees, 0 at 90 degrees, and negative, maximum negative, it inverts the signal at 180 degrees. And this is the result I shown before. So this is the ferromagnet resonance. This is the ferromagnet resonance of berry egg, and after deposition of copper oxide. So it means that the line width increased a little bit, so it's being, the angular moment is being transferred from each iron garnet to the system, to the other system. And this is the same behavior. We also measured the spin pumping signal as a function of the radio frequency power. And we detected also a behavior similar as obtained by the spin-Zibek effect. And we also deposited on top of copper oxide, we deposited a magnesium oxide layer to prevent the copper oxide. In this case, the spin pumping are similar. So what means that this enhancement here is related with the copper oxide presence. So the explanation, to explain this phenomenon, we called this guy here, which was the first author of one of those previous papers, to help us to explain. And the explanation is just this one here. So in this case, when we inject a spin current into the platinum layer, due to the large Miop coupling, the spin angular moment and orbital angular moment are coupled together, and it creates a LS current now, orbital and spin current. And in this case, it due to this it creates a voltage, and the question is how to explain this enhancement here. Then the enhancement which occurs for thin layer of platinum occurs due to the inverse of the Hashbar Hamiltonian effect, which occurs at the interface between the platinum and copper oxide layer. And as the platinum layer increases the thickness, so the current, the LS current, doesn't reach anymore the interface, and it decreases to values of the saturation values obtained for the platinum system. So the conclusions are that in this case, in the second part of our talk, of my talk, we obtained a very strong inverse spin Hall effect in yttrium platinum copper oxide. In this case, the two previous papers, they measured the orbital torque transfer by using transfer moment. Here we are measuring the inverse effect. And we are proposing that due to this large coupling of platinum, spin and orbital states, which exist in platinum, they are entangled. And part of this signal is due to the inverse of the Hashbar-Edelstein effect, which occurs in this interface. And what we are showing you here is that the orbital degree of freedom is play a very important role in the conversion of angular moment to angular moment injection in large Miop coupling materials to charge current. So at the end of the work, we wrote this sentence here, and we are proposing that this result will help to understand the spin orbital entangled physics in no-equilibrium experiments. And it could be important to increase this angular moment to charge current conversion system. So the work was performed by these people here. It's Eduardo and Elias are two PhD students. Lilian performed the STM images. Dong Wu helped us to understand the phenomenon. Joaquin conducted performed the X-ray measurement also, and he helped us to understand this. And I would like to thank you for your attention, and I would like to thank these agents for the funding. Thank you.
Thank you. Thank you, Antonio. Thank you, Antonio. This was a really, really nice talk. I really enjoy all your presentation. I think it's.
Thank you.
I think it's going to be a must-watch talk for all our PhD students. So yeah, I have a couple of questions. I would like to open the session to questions. So if one of you has some questions, you can up your virtual hands or let us know through the chat. So we can start with a question of the conference room, I suppose, or.
Actually, I decided to prepare a presentation most directed to the students. And so I decided to review some base concepts. This is the reason why I talked about so many basic results.
Thank you. Yeah. It was really didactic. So I will start with some question. In slide 19, if I recall properly, you mentioned the self-induced spin Hall effect. So there is not so much literature about that, only 4 papers, 5 papers maybe, but is there any consensus about the origin of the self-induced inverse spin Hall effect?
This is a very good question. Actually, since from the beginning, we discovered that from the beginning of our investigation about this, we discovered that when we have metal system by layer, for instance, permalloy and platinum, permalloy and tantalum, and so on, the voltage signal is normally asymmetric.
Mm-hmm.
And this was attributed due to this spin galvanic effects and not spin, to the galvanic effects and isotropic magnetoresistance and so on. So this is still not well understood.
Okay.
I agree with you that sometimes we can investigate it using platinum and permalloy very symmetric signal, and sometimes they become asymmetric. In 2015, we attributed this effect to what is called the magnetic charge pumping, in which it was measured in different systems. But I agree with you, Luis, that this is still not well understood. It needs probably a very patient measurement to understand it. I would say that it has many origins, which are difficult to disentangle these origins. Sometimes it's important, sometimes not, and so on. For instance, if you use different metals, iron or copper, and so on, the effects are different.
Okay.
So if you would like to get rid of this effect, you have to use ferromagnet insulators.
Okay. Yeah, I understand. Thank you. I have another question, but if I think there is one in the chat from Armando Peso. He would like to know if there is another materials apart from copper oxide, like STO maybe, and also if it would be possible to explore orbital physics in 2D materials like MOS2 itself, which recently have been proved theoretically to display orbital Hall effects carrying orbital polarized edge states within the gap.
Okay, thank you, Armando, for the question. Actually, these results are very new ones. So here in Recife, we are trying to actually, for instance, if you use aluminum oxide, naturally oxidized, the phenomenon happens, but the enhancement is a smaller one. Armando, there is a very tricky question that the people do not understand. Actually, I wrote to Matthias Klau in Germany to know, and actually our co-author do not he doesn't also understand why the effect happens only if we leave the copper to be naturally oxidized. If we try to make a very good copper oxide layer, it doesn't work. So I would say to you that all this this material that you mentioned in your question, probably the phenomenon will happen also. For instance, if you use tantalum instead of platinum, the effect should decrease. The effect should decrease. We have very recent results that shows this really happens. If we put tantalum instead of platinum, that enhancement it actually decreases the signal. Actually, this was also proposed theoretically in the theoretical papers, the 2018 paper that I have shown, which was authored by this guy here, this Don Go. He also proposed that if we use tantalum or tungsten instead of platinum, the phenomena should decrease, because the coupling between L and S is negative. The coupling between L and S in platinum is positive, but in tantalum is negative. So, so if you use 2D materials, probably the effect will happen also, but you have to have oxide materials. For instance, I have seen papers in which the people detected this orbital Hall effect in titanium oxide. Very recent papers also.
Okay. Okay, thanks, Antonio. I have another question. Wait, yeah, I have another question. Is there a way to tune or to disentangle the spin Hall effect from the orbital Hall effects in some material, for example, or some with some experimental condition? One thing that I could think maybe is, I don't know, use a ferromagnetic material in which you can change the orbital momentum, and depending on the concentration or the temperature. But is there a, I don't know, experimental way to tune these two effects, the spin Hall and the orbital Hall?
This is a very good question. Actually, for instance, if you substitute platinum by a ferromagnetic, as you mentioned, right?
Mm-hmm.
In this case, if it has large Miop coupling, probably you will have the coupling between L and S, orbital and spin angular moment. But I'm not sure about the role played by the magnetization of the ferromagnet material. I'm not sure what's gonna go, what's going to happen if in this case. But I agree with you that it should be interesting to try different materials. What is really interesting is that this field is just starting.
Yeah, I agree with you.
If I would advise you to go to the homepage of this guy here, this Go, who is in Jülich, and he has a list of very recent submitted paper were submitted to archive with experimental measurements in this area.
Okay, I will check for sure.
Sure.
Yeah. This, Is there any other question? Yeah, Carlos has a question, so please go ahead.
Carlos.
Question. Well, I enjoyed very much your talk. I didn't understand much because I'm not in the field really. But one of the things that listening to this surprised me is that graphene has spin-orbit coupling, which is not that it shouldn't be large. Why you think
Actually, it's extrinsic effect. Graphene
I see.
intrinsically has no spin-orbit coupling. But if you put in contact with the ferromagnet material, due to the proximity effect, it creates somehow a spin-orbit coupling. This is just due to the proximity effect. Hey, Carlos.
Hi, Antonio.
Hi. Did you understand?
Some
Ramos.
part, yes. Thank you. Yeah, thank you for the nice talk. Really nice.
Carlos Ramos.
Sorry.
We just asked the question.
Well, yes, of course. I understand that graphene gets the spin orbit for proximity effects.
Yeah.
That's
when we measure the magnetoresistance in graphene, just deposited on top of each iron garnet, we measured very strong signal, which doesn't exist anymore if you just by single layer graphene.
Very nice.
Okay, we have a question of Carlos Rojas.
Thank you, Antonio. Really nice talk, very didactic. I enjoyed a lot. I have a question. When I saw one of your result on bismuth, selenium, permalloy, and you compare with the same with platinum and tantalum, I mean, your results are very clear. You have the same sign as for tantalum. However, it's opposite that the rest in the group have reported for bismuth selenide. Usually they report the same for platinum. Do you have some explanation why is this difference?
You mean that there are papers published in which the signal is equal, the signal is the same as platinum?
Right.
Actually, I didn't keep tracking these papers, so I would like to ask you to send me these papers. I'm sorry, I have not seen this paper.
Yes, yeah, of course. I mean, I have also some measurement not published that I have the same sign as for platinum. That's I don't know if this composition, some gradients, some interdiffusion of the interface.
Yeah, because in your case, are the samples fabricated by each one by sputtering?
Yes.
Okay. Yeah, actually, I have not seen measurements of spin pumping lately. I have not seen the spin pump measurement in this sputtered Bi2SC3 material. So I would like to ask you, please send me a copy of this paper so I can take a look at it.
Sure.
I'm sorry, I have no answer for your question at this moment.
No, it's just me neither. It's just very intriguing, interesting to see that it's maybe a composition. I don't know, but they have different.
Because when we sputter, the composition, the target composition in the sputter changes a little bit when we deposit the films. It can be due to this, so we have to go back to investigate this.
Right. I can maybe have another question. So you show nice result on this orbital Hall effect when you have platinum with copper oxide. In the spin pumping, you had a gain of a factor almost 4 or above 4. In the spin civic, a factor 2.
Yeah.
I agree. You say that the spin injection is different. Spin pumping is current, and spin civic is current. But there is a way to exploit this factor. I mean, to quantify some parameter beyond this.
Yeah, this is a very good question. Actually, from the beginning, when we started to investigate materials with using the spin Seebeck effect and the spin pumping, we detected the difference. So the difference, probably from the fundamental point of view, is due to this coherent and incoherent injection. Charles Chen from Johns Hopkins I have discussed with him about the difference. He agreed that there is a huge difference. So in the case of coherent spin pumping, there's a coherent current being injected when thermal effect is not coherent. So probably this plays a very important role to explain the result. And I have no answer for your question at this moment also.
Yeah.
But this is a very nice, you raised a very nice point. For instance, there is a problem, for instance, when we measured yttrium garnet tantalum, for instance, the increase of the line width of yttrium iron garnet is very little compared with the platinum, but the signal is also large. And I have no explanation for that. And I'm using the student to investigate this systematically investigation. So comparing the tantalum, why tantalum, the FMI line width in tantalum doesn't increase as much as platinum, for instance. And sometimes it doesn't increase nothing. I put an E8 tantalum, we measured a very large spin pumping signal, but the line width doesn't increase, doesn't change. This is a trick to me. And I have not seen in the literature that people talk about. Actually, there is a French guy, probably you know, Grégoire de Lubin. Yeah, Grégoire. He mentioned this in a paper, old paper. Okay, I have just mentioned this effect.
Thank you.
Okay.
Thank you, Carlos and Antonio. Is there any other question? Okay, if not, I would like to thank you again, Antonio, for a very, very nice talk. So you are welcome to present your work whenever you want in our seminars. So
thank you for the invitation, Luis. Thank you for the invitation.
No problem.
I hope by the end of the year I'll be in Argentina too.
Yes. We are expecting you for the Spin Argentina. So
great.
We will see you soon.
Yeah.
And thank you everyone for being here. This was the 9th seminar of the year, and I will invite you to the next one that is going to be given by Axel Hoffman from University of Illinois in Urbana next week at the same time. So thank you again for being here.
Luis.
Yeah.
Are you moving to Urbana to spend some months there?
Yes. I got a Fulbright scholarship, and I'm going to be in Axel Hoffman lab for 3 months. I think it will be from January to March to work in STFMR. So yeah, I will be there.
Great! Congratulations.
Thank you.
Axel is a very nice guy.
Yeah. He is.
I'll try to attend the next week seminar.
Okay. You will receive the invitation in the forthcoming days. So yeah.
That's right. Thank you.
Thank you.
Bye-bye.
Thank you for everything.
Thanks.
Bye.